Hello everybody, welcome to another stream. How we doing? Cool. Right, so in today's stream we're going to be starting on blue. This is the main thing. But I want to just quickly fix a bug from the last stream. Well, it's not really a bug, it's just we did something a little bit incorrect. So we added tone mapping. So this image is tone mapped using the ACES tone mapper. So here it is with tone mapping off, here it is with tone mapping on. And, you know, basically, rather than clamping the very bright pixels, it will bring the overall sort of like brightness down and allow for those very bright pixels to have some kind of smoother, like, just to be a lot smoother basically. So there's many different tone mappers. I'm not sure if we'll use ACES, but it's one that typically games use and it's quite easy to implement, so I put that one in. But we've got one problem. If you can tell when we toggle these on and off, that the UI changes as well. Right? I'm tone mapping the full final image and not just the game. So it actually will impact things like the texture viewer and other UI elements, which is not ideal. So we want to just quickly move that around a bit. So I did it at the sort of encode to surface, which was probably at the wrong, at the wrong area. Instead, we probably want to make like a post-processed section, shader or something like that. So post-processing that'll apply like, yeah. So in encode to surface, it just writes out to the swap chain image. But instead, I think what we want to do is have like a post-process shader, which will simply just load in. And at the moment, we'll do the tone mapping. And then it will write it out to probably another 1616 texture because well, it depends, right? Maybe for well, if you write it out to a 888, yeah, you can't do any more processing on it. So let's just do this here. And then when we encode to surface, we'll load in the post-processing texture, encode it to sRGB, and then write it out to the swap chain image. So we've got to make this. So the post-process will now be able to be ran on the scene. What should we say? Yeah, take the scene in as input, and as output, it'll write out post-process to a post-processing texture. Something like that, I think. Right, so let's go ahead and go to the graphics and change that around. Hey, Segfault, how are you? Welcome, sir. It's been a while. Good to see you. Oh, got us Pepsi Max Cherry, as usual. So we have to make a new temporary texture. This one is taking the final frame, which included the UI on it and everything. It's not what we want to do. We just want to tone map the game. because the game is anything which is going to have bright pixels, right? We can add like tone mapping to like the image viewer if we wanted to like custom tone map individual images as like a filter mode, but that's a different thing. I don't want to tone map the user interface as a whole. It doesn't make any sense. So this will be the scene dims. Alright. So we take this with us. Oh, okay, and the input would be on the scene texture. And we'll probably have another one called like the post-process texture. Alright. So we shall, so before you render UI, we temporary allocate final frame, gizmo. Alright, here we go. So after we do the sort of like 2D drawing stuff, we want to temporary allocate a new texture. This will be the post-process texture scene, same dimensions as the scene. And that looks good. I just got to obviously make the texture. So we'll quickly do that. So it's going to be GPU resource ID, one of them. Okay, then I've got to actually create the texture initialization. So just got to find where that is. So this just says that it's a texture 2D and has is a HDR target basically. There we go. So we actually allocated this point in the frame, and then so we could probably at this point in the frame deallocate the GPU temp texture, or what was it called? Gotta go to the header file to find out. Temp dealloc. Beautiful. So at this point we could probably deallocate from the GFX scene texture, because we shouldn't need it after here. And this will give us an error if we try and use it, which I think we do. So we try and use it here. So I'm going to be using the post-process now. And that's if there is no UI on this. If we're not rendering to a UI, if the UI is not rendering our texture. That's right. And so the other thing the UI does, what is it? Is it in the editor? I think the editor puts up an image. Wait, what? It was the material editor, wasn't it? Yeah, here it is, scene texture. So we changed it to post-process. You know, for some reason, my editor can just access my graphics system. Yeah, something I need to sort out. That's kind of internal code, but there you go. But yeah, use the post-process and texture when it puts out to the UI. Excellent. Cool, so I think that's going to fix what we got wrong last time. So now when we open up the texture view, sorry. Right, so yeah, this is ACES tone mapped, you can tell. Now let's open up the settings panel and let's change the tone mapper. Now the UI should not change. It's changing because I'm hovering over it, but let's not hover over it. The borders used to change, but now they don't, which is good. So another way you can tell is if we hop open the, actually no. Not a clear way. Or maybe yeah, you can open up this and you're not seeing it change, but I guess this is black and white maybe. No, the brightness will still change. Yeah, a good example of probably looking at this. Well, the scene would change because you... Oh no, the scene doesn't have the scene isn't tone mapped. Yeah. So a good way to tell, right, is I'm changing the... Oh shit, what did I do? See, I'm changing this behind the scenes, see? It's in the background, and this is not changing. So yeah, that means the tone map is not being applied to the UI anymore, or as it used to. So that's cool. So it's just being applied to the game, as it should be. Nice, so now we've got a proper... I guess I could git diff that for a sec. So we want to just say basically add git commit -a fix tone mapping such that it is only applied to the scene, to the rendered scene. Oh, okay. Only apply tone map. Okay, make it even shorter. Only tone map the rendered scene and not the UI. Done. Nice. Beautiful. So, let's get started with today's topic, that is Bloom. So in the game, I want to have like a material editor. We did kind of get started on it, and we're going to be working on it as soon as we're done with Bloom. We're getting back to the material editor and having more than just these sort of grey ellipsoids, and adding ways to sort of put detail on like textures and things. So if you take a look at the material editor so far, all we have is a way to sort of change these properties individually. This is probably going to go away and probably change. We'll be redesigning it on Sunday, I think, depending on how far we get. But there's like an emissive color. So this is the OKLCH color picker. And you can tell like it sort of like adds, the emissive strength doesn't work. But yeah, you essentially pick your emissive color, and this should, so essentially like adds it. Emissive means that it will sort of emit light. And, so this would have some brightness, and what you should see is some kind of like blurry sort of, this light should be kind of a bit blurry and bright, a bit like how this is, right? It kind of is wider than the actual light itself. And that is what bloom is. There's plenty of different blooms that you can do. We're probably just going to use the one from this. This is one that people use typically in game engines these days, I think. From this Call of Duty Advanced Warfare one. I can give the link. So on my server sometimes on Discord, I post up like interesting graphics stuff that I come up. Well, it's not just graphics, right? If there's some good programming related things, I'll put it on here. But yeah, there's a few good ones on here, like rendering of Callisto Protocol, so we'll look at. I think I might have watched that one. Well, but I didn't go to SIGGRAPH, so I don't. Maybe it was it at the advances in real time rendering thing. I don't know. Maybe not. But anyway, it's this one. We're looking at this PowerPoint here, so I'll share these for you guys there, and you can take a look at in your own time. But the basic idea of how the bloom works is that it will essentially take the scene, it will downsample it, and sort of take some kind of like average whilst it's downsampling to a smaller and smaller resolution, thus making this sort of. Now, what's a good way? I think there's a few good. Yeah, this is like the bloom effect. So essentially do a series of down samples. Yeah, this is the filter actually. Ah, they got a learn OpenGL one. Interesting. Yeah, so essentially you take like a special, you do some special sort of like filtering every time you down sample and produce. Ah, maybe this is like it. Yeah, so you downsample it continuously, and notice how it sort of gets a bit wider, right? Okay, let me bring it here because it might be a bit in the way. Ah, here's a good image. So you downsample, essentially it will get gradually a little bit wider, and then you sort of like upsampling and combining them in a sense. So you will create a sort of like, and the one that the sort of the lower mid will not contribute as much as the ones sorry, this is the the more smaller resolution MIP will not contribute as much as the higher resolution MIPs will, and you'll get a sort of nice bloom effect. Now this streaking could also be probably seen as like be done in bloom as well, I think, these days, but we're not doing that type of one. I think that's more of like a lens flare effect that they've done on top of that, especially with this sort of thing here, this lens flare. But there is a sort of one they do in the new Unreal Engine called like FFT bloom, and we won't be doing that one, but there is like a GitHub for it, and you can look at it. Basically, where you get these sort of like star patterns and stuff. Hey, Damn it. Hey, how's it going? What site would you consider a great place to Vulkan tutorial? I don't know if there's really, I don't know of many good Vulkan tutorials, to be honest, because it's been a while since I've actually learnt Vulkan. But yeah, I don't know how. Like, I could. Yeah, I don't know if I have a really good reference, to be honest. But if you have any questions, you can feel free to reach out to me because I know Vulkan like really well, and I will happily answer you any questions on the Discord channel there. But what I would recommend for you to do is, first of all, you get started with compute, and you just get compute shaders working because those are the easiest thing to get up and running, and just render some like full screen rectangles or something like this, right, onto a texture, and just get that working, because that alone takes time, but it doesn't involve all the sort of like rasterization state stuff you have to do. And then afterwards move to getting your move and get your triangles working and stuff like this. But I wouldn't bother using vertex buffers, because vertex buffers require like you to use a vertex buffer type. Just use a storage buffer as you would, and just read in the vertex data manually. It means you can do some custom packing, and you don't have to put the vertex format into the pipeline state object. You'll see that later on. You can just skip all of that and just pass vertices as data. What else? I will also make sure you're using the dynamic rendering API and not using render passes. Render passes are very complicated, and you pretty much don't need them if you're just targeting a desktop. So search for Vulkan dynamic rendering, and this basically gives you a sort of a similar API to DirectX, where you just set render targets directly. So rather than doing a begin render pass, you just say begin rendering, and then you sort of set attachments. Attachments means render target, same thing. And use this API instead after you've got your compute thing working. Then you can do proper, use the proper rendering API to do some triangle rendering and stuff. This is a lot more easier to get up and running. Render passes require just a lot of extra crap, and it's not used at all for PC, I think. Pretty sure. Or if it is used, it's very negligible, shall we say. I think what they do on... I think using this dynamic rendering actually will probably be faster when you give it to the driver, because the driver, when you give it a render pass, might have to do this whole sort of like check. Use the... Oh. Yeah, I might just do more things. Yeah, just use that feature. To use Vulkan 1.3, you got to enable that rendering feature, and that would make it a lot easier. And what else is there to make it easier? Any more common pitfalls? Oh yeah. Here's another one. Descriptor sets are... Managing descriptor sets in Vulkan. So when you eventually learn what descriptor set is, they're actually very basic, but trying to understand them might sound a bit weird when you've got descriptor sets, descriptor set layouts, and descriptor descriptor pools and stuff. What I would say is, it might be a little bit confusing, but... So, okay, let me just tell you. When you try and manage your descriptor sets, it's very complicated to solve that problem, especially when you're just starting out learning Vulkan. But if you use a thing called bindless descriptors in Vulkan, it allows you to just make 2 descriptor sets, and that descriptor pool and descriptor set layout, you just need one of those, right? And all you do is you switch between these 2 descriptor sets. So one you upload from the CPU whilst the GPU is currently using the other one, and then you swap them around, right? That's a common thing you have to do in Vulkan sometimes, is the GPU is using one and you're using one on the CPU side, right? And with this sort of way of doing it, you don't have to manage tons of these descriptor sets and descriptor pools. It's a very complicated problem to solve. But there's just a little bit more of an initial setup, and the API is a little bit weird as well when you try and set this up. But you know, as soon as you have it set up, it's amazing. And it means you can basically refer to resources as an index. So it's incredibly powerful because it means you can literally pass indices into buffers, and that will tell, and you can use that to access all the textures you ever want, all the buffers you ever want in your shader code. Incredibly powerful. It's what I use. It's what I built my compiler around, actually. My custom C compiler just uses bindless all the way, and that's how we do all of our fancy cool stuff in the game. I accidentally dropped a crumb in my keyboard. Let me just deal with this. Hang on a minute. Big crumb. 2 big crumbs. Right, I think that does it. Yay for mechanical keyboards. We can pick the keys off. Hey Lupo, hey there Cranston. Oh, okay, you've tried with the random passes. Oh, yeah. Right, fair enough. Well, at least you got started and you have a bit of understanding of what I'm saying, which is great. I've not listened to them myself, not even heard of people reading the Vulkan tutorial. Vulkan guide, none of Jill style approach. Right, yeah. Yeah, I guess you could try those out. I think I tried some of those maybe back when I learned ages ago. Hey, Lupo, hey. I mean to look at bindless. Good reminder. Yeah, it's a blessing. Bindless is amazing. Bindless is amazing. What kind of switches? So this is my first mechanical keyboard, and they're not the sort of hot pluggable switches, so I just got them. It was choice between red or blues, and I just got the red ones because I didn't know what they were like, and you know, I like it. Maybe I should try other ones out some other time, but yeah, so they're just cherry reds. So yeah, this was the other sort of bloom, which we're not going to do, but you can get there's this other type of bloom called FFT bloom. It's like a fast Fourier transform. That's the one. And essentially you're converting the image into frequency space, so all the sort of, you know, that sort of sine wave frequency space type of thing. It's not something I fully understand, to be honest. And then you're essentially applying in frequency space like another image, which is called like a kernel image, I guess. And then it will essentially apply it to everywhere in the screen at once, and they can also do like a blur on it at the same time as well. And it means you can sort of like then turn it back from frequency space to image space, and you get these lovely like bloom things. So it means you can make your own little custom images, and it will essentially like apply them everywhere, which is kind of nuts and insane. Like, yeah, it's pretty smart. But we won't be using this because I don't know, you know, people do those like sci-fi streaks with them as well. You know what I mean? The wide ones, not just the star ones. So I think there's a YouTube video on it as well, but it's something I want to probably understand more before I actually like did it. So we're not going to do this approach because it'll be a little bit more hands-on. I think it's a little bit more computationally expensive as well, because apparently turning into frequency space is a little bit more intensive, but it might be, but yeah, something to look at later perhaps. Right, so now we've been over all the preamble. Let's get on to how we're going to do this. So we need to basically downsample our scene. So let's create a texture with 6 MIPS, because that's what this presentation says we should do. We're following the Apology Advanced Warfare ones. So they've fixed, there's a bunch of problems like people get with like fireflies and, you know, like basically flickering and stuff and all this. And yeah, so we need to take our, so you get a threshold. You take a threshold of the image to just expose the bright spots of the image, and then downsample. Okay, so let's just start there today and see how far we get. So I'm going to create a new texture. So we'll call this the bloom pyramid or whatever, or bloom texture. So it's just a downsample thing, right? So we're just going to go ahead and find this one. You know, I don't know what I want. Let's just do it there, right? Yep. All right, texture 2D. It's going to have MIPS though. I'll do that later. Yes. So it's temporary, so it means they're allocated during the frame. And we want to have it at 16, 16, 16. Right. So before the post-processing pass that we did, the new one we added just a second ago, this is where the fun begins. So we're going to do some bloom. So maybe, just maybe, we make another function just to make it a little bit easier. Graphics render bloom, shall we say? We'll call it that. Seems sensible enough. Because I think it's going to be quite involved. We're going to have some kind of like custom shaders and things. And these are, because I don't think we can leverage that single pass downsampler. We might be able to, but if we did that, it might introduce bugs. So it depends on how performant this custom downsampler thing is. So we want to create a new GPU temp texture allocate graphics bloom. What is resolution? Well, we probably want to round up to the nearest power of 2. So that's sort of power of 2. So if we round up to the nearest power of 2, that will allow us to not get any sort of odd numbers except for in the final MIP, which will cause sort of like, which will make the image represent more space than the previous image did, because you'll be, it wouldn't be exactly in half, it would leave out the previous top row of the pixels from the previous frame or something like that, and essentially stretch the image. So that's not very good. Well, it won't stretch the image in the down sample, it's just the space that it would now represent would be a bigger area, shall we say. So yeah, we want to make sure that we do a power of 2, and that way it's always divisible by 2 until it reaches 1, which is ideal. So we want to use graphics scene dims. That's essential theorem in Fourier signal analysis convolution in the spatial domain. The sum of patterns we saw earlier can be one-to-one mapped to matrix multiplication in the frequency domain. Right. Pretty nuts. Pretty bananas. Yeah, something I need to learn more of, to be honest. Sounds super powerful though. You know, it's clever. So the dimensions in this case, it's not occlusion anymore, this will be the bloom dim. So really we should probably stick that in the, well, in a couple of places. But let's just get it initialized here quick. So bloom dims, and then the MIP levels. So this Call of Duty Slides was recommending that we use 6 MIPs. It's somewhere. Honestly, it's not ordered nice, I guess. It's not ordered from beginning to end. Like they have like improvements later on to the steps before, so it's a bit all over the place. Not quite in the order you want. But I've had a quick look. But yeah, they recommend, I think it's like 6. Right, there's the references. There's like, it's just somewhere around here. There's like 6 MIPs. That's what they do. So let's try 6 then. So maybe we'll make it a constant or something. All right. I don't know. Why would we do 6 MIPs though? So there's the other sort of blog that we saw. This is an interesting one. I don't know about this. Oh, they're talking about the Call of Duty method, right? My method. Look at this guy. Has his own method. This is typically what I would do. But for this thing, I just want to... Oh, then they put in the ghosts and halo. Oh, so they're combining the lens flare stuff into it. Works in 8 steps, down samples 8 times and up 7. Right, so they combine that last one. Right, so it might be a case of just seeing... So maybe we can work out how many we want to go down to. Maybe go down to like an 8x8. Yeah, maybe we say like, you know. So I think there's like, I've already got a function called like max mips from dims right. So I can just put in the sort of the balloon dim .xy. And so essentially, that's if we did a full depth mirror down to 1x1. So if we said down to about 8, so MIPS max from dims. So if we take away 1, that's a 2x2. 2 is a 4x4. 3 is 8x8. So yeah, we've got to be careful on like if we reach. You know, what happens if we make a super small image to render to, right? There's lots of these problems that start to arise with these sorts of things. So maybe we should make like a new function called like MIPS. And then we have like a so you got your like original dimension, or the actual dimension of the image, and then probably like the final dim. So we had that. We could put all the sort of logic. So be the function above. Then you say max so I guess you like log to that as well. Final dim log 2. So if it's 8, it's 3. If it's 4, it's 2. Right. Well, then you gotta add 1. So if it's 1, 3, 0, yeah, so you gotta add 1. It's like the bit index. Yeah. Cool. So nice. And then what you can do is say, well, if MIPS is less than final, then you, okay, greater than, yeah, then you return MIPS take log 2, else return 1, I would say. If I buy a blue switch keyboard, would that bother people in the room next door? Yeah, I think they're louder. I think brown's the loudest. The difference between, you had your MX brown a while back, it was okay because they liked it much. Nowadays, There's so many mechanical keyboards with different kinds of switches. Right. Yeah, the red one's already kind of quite loud. You know, it might get even, you know, maybe the blue's even louder. I don't know. They're the loudest, right? It's funny. So now we've got a more safer function, a bit more readable function as well. Right. So now we literally have our number of MIPS. Look at that. Pretty nice. So this will return 1 if it will return at least 1. And it scales depending on the resolution, right? Yeah. Yeah, I'm not sure. Maybe that's not a good idea. Or maybe we should say like, I don't know. We can change it, but at least we have that function there. It'll be handy. So array layers 1 as well. So there we go. So allocate the bloom texture and kabam. So the next thing we need to do is actually get these in properly into the graphics globals for the downsampling, at least, I would imagine. It would be nice to have in this. In the graphics globals, it's just available in every shader. You know, it's pretty nice. So we're going to go ahead and put in bloom dims and probably the number of MIPS as well. That might be handy. And so that is accessible via graphics globals. It's a pointer we can set, and this is something that is going to get uploaded when we submit the frame. And bloom MIPS count. And voila, so it's got to do .xy because then it's a vector 2 instead of a vector 3. Nice. So the next thing what we need to do is so I think what they basically say is, right, the standard way is to take a threshold of the color and then basically downsample the input image, like gradually down all the MIPS, upscale it up all the MIPS, and add the MIPS to the original image, and then sort of blur somewhere. That's basically what the traditional method is. So they haven't changed this threshold one. I think they've added some insights on how to make that better. Oh, hang on a minute. Maybe not. Thank you, next slide. So apparently their method aims to improve the perception of a wider dynamic range. Non-threshold color used as input for bloom, as suggested back in 1997. Almost as old as me. Our dynamic range, physically based rendering is very wide, aims to yield natural results as if we're looking with our eyes. Okay, very freaky. Right, so apparently this talks about the temporal stability. So sources of instability is filtering through downsampling. Information must fit into the lower MIPS, and upsampling information must be used. Must be correctly synthesized. Firefly's very bright subpixels. So filtering possibilities, they say there's this one where you downsample, then you filter each MIP, and then upsample each MIP. There's two where you downsample and filter at the same time, and then upscale. 3 is downsample, and then you upscale and filter at the same time. So filter means like blurring it or something like that. And then 4, they're sort of, well, I think maybe I got the filtering a bit wrong. No, maybe it is a blur. Yes. So they're saying they're doing it as you downsample and as you upsample. So this is where I don't think we can leverage the single pass downsampler because they've got some extra bells and whistles they do, extra tricks. Filtering both when downsampling and upsampling is key, according to this person here. Downsampling for preventing aliasing artifacts and upsampling for image quality and smooth results. You can use the filter to blur the image and to analyze or synthesize at the same time. Okay, so yeah, they do the blurring by doing a bunch of texture samples and combining it, basically. I think that's why they're using the word filter. So here they're basically saying like a bilinear downsampling and upsampling has low quality results. So a bicubic filter does not work well due to the negative lobes. Right. I have no idea what that means. The Gaussian is possibly the best option. So they talk about some previous examples in here. Yeah, so we just downsampled, we'll get a 2x2, and we'll average 4 texels. That's if we use our single pass downsampler. What they're saying here, so an improved method is to take an extra, or do a 4x4 instead, by doing 4 samples, right? So it mitigates some of the issues, but it doesn't completely fix them. But what they suggest is this crazy thing here, where they just sample essentially a 6x6 with 13 bilinear samples, right? So it's 36 texels it will get. So yeah, if we were to get started on this now, let's just double check. They're saying no non-threshold color used as input for bloom. Ah. Well, how interesting. So they're not doing a threshold. So let's just get started with that, because we could always add a threshold in afterwards, right? Let's just get the downsampling, this special downsampling working, and the special upsampling. And then we can, So we're going to do a copy. Texture copy, I think I called it. Radio. So let's just do a texture copy. Step 1. The source will be the scene, and the destination will be the bloom texture at the first MIP. So let's just run this. Well, we can't just run. Oh yeah. Of course we can. Oh. Right. So render bloom is going to run, and let's just look at the texture view and make sure the thing just works as we. Oh, Oh, there it fails. Have I put an extra 1 in there? Jeep, like in the string thing that I'm using to, what was it 1297? Hmm. Oh, I didn't put an X in there. Alright, no wonder why that looked a little weird. Alright, that's good. So, what you saying? Destination. Did I get the source and destination wrong way around? Oh, I did source bloom rather than... Right. That makes a ton of sense. So yeah, the source is the scene, the destination is the bloom texture. Okay, okay, okay. Oh, what is this complaining about now? Oh, for crying out loud, I had an extra cursor going around, didn't I? I had an extra multi-line cursor going on the other thing, so... Okay, destination is bloom. Right, that'll do it. Cool, so let's open up the super lovely texture viewer. So there's our scene image. Texture viewer. We should have a bloom now. We're starting to get a reasonable amount of these. Okay, so you know the white levels are a bit, but yeah, they're fine, right? So we've got some uninitialized memory here. This is okay because it's at the boundary, right? If we look. Well, yeah, we don't know what the resolution is, but that's about right. It's about right. And then if we look at our lower MIPS, we've got, yeah, they're just black at the moment, but we've got 8 of them, and that gets us down to a 16 by 8 by 1, and that's right because we want to go to about an 8 by 8, so it's gone down to at least as low as 8 on a dimension. Cool, so step 1 complete. So we've populated that, so now what we're going to work on is the special downsampling. So we need to do this. So every 6 by 6 you're doing a bunch of these samples. Now we're using compute shaders, so we could probably share a bunch of these if we were smart. So when you're, it's got to be, yeah, it's got to be careful here. So for a 6 by 6 you do this sort of like tent filtering thing. We could probably preload them into LDS and you'll get some level of overlap. And that means you can do the so you can pre-sample them, load them into LDS memory, and then reuse them. Right, so we're probably better off using 16 by 16s. Or maybe even more. How does the single pass downsampler do? What does it do? Does it use... I wonder what size they use on that one, AMD. Graphics, internal shared. What was the LDS things? 16 by 16. Alright, okay. Alright, I got me some ideas. So we can make like a bloom section Maybe. Right, shaders. So I've got just a bunch of like renderers and things that are just loosely at the bottom, which is basically everything. Right, there's this BVH section. That should go soon, really, because I'm not using that anymore. Alright, is everything on... Right, apparently everything's under the BVH section in the code, but anyway, the more you know. Right, so above here, that's all the... Oh, is this the material stuff? Oh, for crying out loud. Maybe not. Right, occlusion. Alright, we'll stick it around here. So, I'll call this the bloom section. So, we'll have a custom... Right, bloom, down, sample. So I think what we'll do is we'll make it a 16 by 16. And that way we can share a lot more samples. So the idea is we need the 16 by 16 will be on the MIP underneath. So say if you're downsampling to MIP 1 from MIP 0, MIP 0 being the highest resolution, you will have 16 pixels along MIP 1. So you're essentially looking at 32 pixels in MIP 0 and doing a sample in the middle and then storing them into LDS memory. So we'll simply make a new structure, bloom, downsample, LDS, and just chuck in there, right? This is to be shared between all the threads in the thread group. So it'll just be one of these. So that'd be your colors, I guess. Do we English it or do we American it? No one knows. So yeah, 16 by 16. And we'll use so there'll be the bundle constants will be here down sample BC. Nice. Okay, so we'll probably pass in another number of MIPs as well. Oh, sorry, the current MIP that we're looking at. Yeah, they'll probably come from here. Source and destination textures. Yeah, they'll be passed in. Right. So preload into LDS. I guess we'll start off with that. So what you need to do is we would simply just... So we'll have our sort of dimensions of the destination image. So this would be, let's just imagine we're downsampling from MIP 0 to MIP 1. So you get MIP 1's dimensions. And then all you would do is take the... So we want to find our sort of like source coordinate that we're going to sample from. So that will be whatever the... Oh, we don't need the dims. Alright. Don't mind me. Destination coordinate will be the dispatch index .xy. Then, because our source is twice as big as us, all we have to do is do a multiply. Now I think we're better off making these floats. because then we can turn them into UVs. No. We'll do that. All right. Multiply that by 2. And then so we need to put in a control barrier to make all of the threads block here. So it runs in wave 32s, right? 32 threads in a single wave that run in lockstep, but there's many of those that'll be running to fill up this 16 by 16 group. So 256 threads. So we need to make sure that we flush the caches for the other waves for the dispatch group after we've waited here, always waited here. So this needs to be made a global. Bloom downsample ODS. So what we're going to do is do that texture sample and store in here. So it's got me thinking. So say if we're going to, I've got to be careful, right? So at most you need an extra. So if we're trying to do this pixel here, so this black border is in the lower resolution, right? And these grayer ones are in like the higher resolution. These grayer ones are in higher resolution. So you only have one to your left. So what we actually need is an 18, right? One on each, so an 18 by 18. Okay. So in which case we need a for loop. No biggie. So I actually did this in the visibility buffer AA, which I've been working on some custom AA thing. So here's some code I made earlier. Just plop it in and we'll change it. It's going to be much more simple than this. So this sort of like LDS base coordinate. So where's the base coordinates for this LDS memory, I guess? Do we need that anywhere in here? Yes, you might. Hang on, is there a bug in this code? Oh no, because I did a take 3. Yeah, so we need to do a take 1. So it's groups of 16 by 16 pixels, but we want to step back by 1. Yeah, that's good. And I did the Morton curve on that to get, just so that every 4 threads, it goes into a 2 by 2. So it goes into a Z pattern. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there's this sort of like micro Z order as well as like a macro sort of Z, and it keeps going and going and going like that. So that just makes it so it's more optimal. And it's structured like a pixel shader would be. Okay, so from the base coordinate, we want to go up to, rather than 22s, we want to do 18. Okay. And so this gets us the coordinate within the LDS memory. And if we go outside of that, just don't bother doing anything. Then we calculate our actual pixel coordinate on the screen. And then this is where where the magic happens, where we do our sample. So we do a sample, texture, 2D, and we want to sample a... Why can't I... I want to do the MIP bias. This is what we want. Float time. Yeah. Alright, got it. So the texture is going to come in here. This will be the source texture. And the sampler might as well come in here as well. I think it... I don't know, did we do like a black border? Let's look at the Vulkan sampler. I've not really got it. My samples aren't really that configurable at the moment. Opaque black. Yes. And then I've got a clamp. Yes, so I think I can just leverage the... clamp linear sampler. And that will be what we want. Okay, so that will be the... Then the coordinate would be next. So we've got to actually produce the UV here. So the UV... So in the... Got to be careful though. So this is going to be the coordinate in destination space. Is that right? No, source. Oh yeah, and then to get into source, we need to multiply it by 2. So we're trying to color this sort of black pixel here. So it will have a sort of lower right in integer space, basically. It will be talking about this pixel here when we've times it by 2. Right? So to get the UV, we will need to add 1.5. Because, wait. Yeah, because we... oh no, just 1. So we'll have... It'll be kind of be down here, right? So it'd be 2 across, 2 up. So we need to add basically another 1, and then we put our sample around there, I think. Is that right? Can I just double check? Well, maybe this isn't... Oh... Yeah. Okay. Yeah, so we're just grabbing the samples at every... Yeah, this will work out perfectly fine. So we just need to add 1. And I guess we'll put a comment in because it's a little bit... You look at the code and be like, is this right? Is this wrong? It won't be very clear. So we want to sort of add... After casting to a float, the source pixel coordinate, we want to add 1. And then do a divide. Well, we could do the add 1 here, maybe. Yeah, maybe add 1 so we are in the center of the 2x2. Okay, and then the UV then will be a divide by So I don't need to do a point. We don't need to do a 0.5. To get it into the middle of the pixel. Okay, so that'll be casting it's the dimensions of the source image. The dimensions of the source image. Cool, so I get your UV, and then the MIP bias will just be 0. Or would it be the MIP? Ooh. So it could be a texture view. You know, we could have so we could have like a sample texture being passed in. And then you pass in a MIP bias on that. Like a source MIP or something. Sample MIP. Or it could reuse the same. No, yeah, okay, we'll have separate. I guess that's the way we'll do it. Okay. Alright, that looks like it's going well. So this is going to preload for every pixel. So if this sort of black border here, that's the source, or that's the destination image. So it's MIP1, for instance. The smaller one is MIP0, which is the source image. So for every pixel in the destination image, we're going up into the source image resolution by multiplying by 2, then adding 1. Sampling the 2 by 2 and taking an average, right, just by doing a regular clamp linear sample. And we're going to store that, right, into G bloom downsample colors. We're going down into completely. All right, LDS coord, that's it. So LDS coordinate.y, LDS coordinate.x, and we're going to store the result of that color. So we could probably actually pack it, do a pack here, just so we save some LDS space maybe. So this is the color. So we'll do a lovely pack float 16. Because not all hardware might have a lot of room in this LDS memory, and if you're using like a full-on, 16 bytes per color, and we've got an 18 by 18 of them, that can get quite, it's quite. So we had 16 times 18 times 8. Hang on a minute. 18 times 18. That's about 5,000, about 5K. Whereas if we dropped it to 8 bytes, so 8 times 18 times 18, it's about 2K instead, 2.5K instead. So, wait, how much room have you got in LDS memory these days? Yeah, I don't know. Maybe this is pointless doing this, but we'll see. So we're going to pack it, and then we'll unpack it later on. So this means now we can share all of this pre-sampled data when we do the special filtering here. So for every pixel now, all of those sample locations are preloaded. And now it's just a case of combining for this center pixel, grab all of these locations. Hang on a minute. This isn't enough, is it? Is that right? That one. We haven't got this one though. Yeah, I think we gotta get... So it's at every pixel within the destination, within the source location, isn't it? Ah, crap, we did mess that one up a bit. Right, so if we increase the resolution of this, or we... Okay, so I think we need to increase, so that make it... Yeah, so it's 36, isn't it? So that's going to times it by 4. So we're like 8K, it's quite a lot. So if we make it 36 by 36 for 16 by 16 pixels, or we make it 8 by 8 pixels, and then it would then be a 8 by 8 plus 2 on each side, which would be 10, times by 2 would be 20. So that was probably better to do it as an 8 by 8 then. And then, yeah, okay. Because I think there'll be too much LDS memory we'll be using. Alright, so let's try that one again. Slight adjustment. We're not doing... So each of these sample points is actually in the higher resolution source texture. So these are the source colors. And we've got each... Right. Source colors as a 20 by 20. Is it 1 pixel each side? It's 2 pixels each. It might be 2 pixels each side, which would put up to 24. Interesting. Because you've got this... Yeah. There's 2 pixels each side, okay. Rightio. So let's try that one again. So rather than 18, it's 24. If we go outside the range of that, we just won't initialize the memory. Is that a good idea? No. Right, so we've got to make sure that... Okay, source dims. Or destination dims, that's it, isn't it? Okay, something we are missing from the bloom is we kind of expect all of the bloom something I did miss is a texture clear. we kind of should make sure we clear the original image, because if not, we're going to get some of the uninitialized memory leak into some of this here. It's got to be a little bit careful. So we're just, this is going to clear all of the MIP levels. It's a bit exhaustive, but we can optimize it later. We'll go overlay every part of the renderer and optimize it at some point. Right, does the job. Good, good, good. What do I want? Oh no, that would just clear a single MIP. Bang. Alright, it's already optimized then. Cool. It's just a custom shader. Nice. Okay, so we're going over every single... So did we go over 24? Yeah, it's a good point. So LDS base coordinate, it's in the destination the source texture. So it'd be multiplied by 16, I guess. So it's actually multiplied by 8, then it's multiplied by 2. Let's just do that manually. And then we take 2 pixels. And that will get us the base coordinate of where this LDS memory represents. Okay, so it's 8 times 8 is 16. Is it 24 or is it 20? Yeah, because if it's a 16 by 16 range before you have the border, then you're just adding 2 before and 2 after. So it's 20. I think that's right. Yep. Okay, so that's in the... So that's the base pixel in the source texture, where this LDS memory is caching. The local coordinate I think we'll just call it local chord. Okay, we'll live with that one. So go over all 20 pixels. In strides of 8. Because we'll have an 8 by 8 threads in a thread group processing it at one time. Then we say okay, get our source coordinate. So our source coordinate, I think, is this one. And if that goes outside the bounds of the source texture, oh no, sorry, if it's inbounds, then we do this lovely code here. Where we convert that into a UV and then do the sample and then pack it down to save some space and put it into the LDS memory, then wait here. Perfect. Alright, so the next thing to do is, I guess, will be a sort of like source coordinate, which would be the... No, so if the destination coordinate goes outside of the destination dims, then return. Good, 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 good. Okay, so now I've just seen right, I've got to be but it doesn't do these ones here, which is interesting. And it doesn't do that one there. So I wonder if we're sampling on unused things, really. This one. So we're going to be sampling like this one here. So if we have like a 16, what's an 8 by 8, isn't it? Yeah, but if you are coloring this pixel here, you'll be this will be moved to the left by one. And so you would be getting these corners. You still won't be getting this one up here. And this one down here, you still won't be, because this is where it is, right? You won't get this one here and this one here. You never do that. Right, maybe we've got to be a little bit clever on how we do these. Okay, so maybe at this destination image, or it's bigger. Mm-hmm. Ah. Yeah, so maybe the showing is going to be, maybe we're oversampling. So I think there's oversamples here. So we've just got to be careful, right? I think, so we'll carry on, but to do, we are oversampling. Maybe what we can do is figure out how to know which ones are definitely not going to be sampled from and just don't do it. Right. Okay. So let's just get on and get the thing written out, and then we can see if it looks all right, and then fix that there. So given a pixel, so the black border is the one in the destination text, right, the lower resolution MIP, so MIP 1 for instance, and these grey ones are MIP 0. So we need to take, to color in this sample, or this texture pixel, we need to take all of those sample locations, which we have in this grid here. So we have like a LDS. So we'll need to be able to get the coordinate in wait, is that a bug in this thing? Add 3. Oh yeah, no, you need to add 3. That's right. So in this one we've got 2 by 2, so you need to add. So your local coordinate is 8 by 8, but yeah, in the source image it's a 16 by 16. So you need to multiply it by 2 to bring it up into the 16 by 16, then add 2. Okay, so there's the LDS coordinate of the pixel you're trying to shade. So we've got, so we're trying to shade like this pixel here in the source texture, in the destination texture, because it's smaller. In the source texture that's bigger, we've got this one down here at the moment. So what we can do is we can now add 1, add 2, then add 1, so that it's in the center. So make it so center inside the 2 by 2, just like that. Cool. And now it's just a case of basically taking 2, grabbing that 1, right, and doing the weighting. Okay, so the weights are all sort of here, right? So you've got a couple of purples and blues and things. So what you need to do is, so all the red ones are 0.5 contribution. Right, so let's read this over a bit. So custom handcrafted 36 texel downsample, 13 texture fetches created by a weighted average of 1 pixel shifts. Of a H 4x4 box. Intuitively, the overlapping further breaks the grid nature of pyramid approaches, works better than comparable size filters, eliminates the pulsating artifacts and temporal stability issues. So this is 4 separate fetches. So okay, how's there 13 fetches? 3, 6, 9, 10, 11, 12, 13. Right. But then it's 36 texel. Okay, good. So I read that correctly. So these, so we need to take the, so the sort of the, these are only used once and they're 0.5 contribution, whatever these ones are. So they are basically +1 on all that. Weighted average of 1 pixel shifts, right. So we'll get some sort of like color. And we're just going to initialize this to 0. And now we're just going to accumulate all of those colors. So it's going to be using color. So we get all the 0.5 ones. There'll be an overall type of weight as well. Total color, total weight. So total color. If I understand correctly, the red ones are not uniformly sampled, right? Ooh. Uniformly. What do you mean by uniformly sampled? So they're a so there's 4 separate samples and it's done using a bilinear sampler. So it's getting these 4 texels and producing a result for those. These 4 texels producing a result for that. These 4 and a result for that, and so on. Then you're getting these and adding them together pre-multiplied with a weight of 0.5, right? That's the way I understand it. Is that what you're referring to? Something like that? So add, yes, we add the existing color. So I could make a macro for this, right? But I guess it'll be fine. We'll see. So then we do an unpack float 16. We're unpacking G bloom. Now we're going to do LDS coordinate plus dot y plus something, and then LDS coordinate dot x plus something, and it's ultimately what we're going to do. And then we need to actually multiply that by some kind of weight. So really it's probably better off to say like accumulate color, and we just put this, or fetch color, so it would be a sort of like an offset. Yeah, but imagine you have a grid of 6 by 6 of these. There would be no reds between those. Oh yeah. So this is where I've done it slightly wrong in the preloading code, where I've just preloaded every pixel. So I've preloaded every pixel from the source texture, which is a little bit wrong. But they are 1 pixel away in some regards diagonally, but not. Yeah, so there's some sort of holes in them. So this is where in some of this preloading code we've done into LDS memory, we've got to be careful because we're oversampling here where they're never going to be red. So yeah, that is correct. So when we so in the source texture, this black area, if we go over to this one here, the red ones will be here, 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 and here, right? So they would never, the red ones will never touch this pixel, that pixel, that pixel, and that pixel, basically, yeah. Naively, I would expect this sampling pattern would repeat for every output pixel. Yes, that is correct. Every output pixel. Yep. Yeah, I wonder what I could do to improve. Yeah. Hmm. Yeah, I wonder how we could put it into LDS memory. But for now, we could just start with this. So, a sort of an X offset and a Y offset. And then some kind of like weight. Easy peasy. So we're just going to then multiply at the end by some kind of weight. Crap. Well, that worked out well, didn't it? See, I think we'll say this will go here. Oh, it's not liking that, is it? So something's a little off here. Right, well that's buggered. It's alright, so brackets are right there, that bracket matches that one, that bracket matches that one, that bracket matches that one. Jobs are good, and this is the Y offset, and then this is the X offset. So it should just be a case of saying fetch color. Well, maybe we say accumulate color. You kind of want to accumulate the weight as well, though. Sorry, I did that wrong. So it's multiply this by the weight and then add. That's it. Cool, so that'd be a... And then total weight is plus equal weight. Nice. So now at the end we'll undef fetch color. Well, let's be accumulate color now. Okay, getting there. Right, so we'll say accumulate color. So these would be the ones where the red ones, for instance, this would be 1, 1, and that'll be the weight of 0.5. Because they're sampling between pixels, I guess they're relying on the texture sample hardware to do the interpolation and caching as a side effect. Yeah. I would also expect the weights to be pre-scaled to the sum. Do sum to 1. Oh, right. So I won't need to... Right. So I would just need to multiply... Oh, they do, don't they? So I don't need to do a divide at the end. Neat. So there won't... Yeah, so I won't need to do a divide then. Awesome. Pretty sweet. Yeah, so accumulate color. Maybe I can move this out here then. Alright. Seems alright. So... Well, no. Because if you've got a bunch of 0.5s, Now I'm confused. Yes, so these are not four 0.5s. I've got it completely wrong. I see how it works now. So this is, so at this, okay. I was misreading the image. When you sample this location, you're getting these 4 pixels and you're getting a weight of 0. And then you multiply that by the result of that by 0.5. Okay. So, right. So you are putting it in the oh, damn it. I think we had it right the first time around then. Okay. So then that one, there's the center. Okay, okay. This position gets you those 4. Right. Okay. So you're doing... Alright, this is easy enough then. We can fix that. Right. So in the source, in the destination texture where it's smaller, yeah, 1 pixel offsets. So it's 1 pixel offsets in the destination, sorry, in the high resolution source texture space. So all you need to do for an 8x8 is you need technically a 18 by 18. Because it's times 2 to go from destination to source, and then plus 1 for the border, where you take the sample points, and that will then sample 1 extra 1 by 1 or 2 by 2 around. Yeah. Also, I would effectively weight per sample. Sorry, so the effective weight per sample is, yeah, do it before, but I guess it's saying it's best to do the multiplication after accumulating the samples. Yeah. Yeah, I think so. Yeah, I think that's right. Yeah, that's definitely the way it is. Right, this is good then. So we're doing this in... We're still sampling in the destination space. So all the LDS memory is doing is caching the samples such that when we do... We just look up into the LDS at all the neighbors around us and just grab them when they're already pre-sampled. So you're getting a lot of... It's pre-cached into basically L1 memory rather than going back out to the texture again. Essentially, it's cached locally. So it should be better. So 8 by 8 times 2 to get into the 16 by 16. Then you want to take away 1. And that's the base coordinate. Stepping groups of 8 by 8. And then... Okay, this is just got to get right. So you're doing it on... So if this was the final... Wait a minute. So if this was the last pixel... Well, this was the last pixel. This black one was the last pixel. It's lower left origin when you sort of refer to it in this integer space. So you times that by 2, so that'll be the base. Yeah. So I don't need to do a take 1. I don't need to do a take 1. Which means I don't need a 1 by 1 then. Huh. Okay. So anyway, 16, 16, 16. So we just had a sort of a 1 by 1 image we was downsampling to. The source that it's coming from will be a 2 by 2, and we'll be using these 4 locations to sample from, and it would get the bilinear. Right. Okay. So then it would be at the corners. Hang on a minute, we've got to get it right. So there's no... We should allow up to the edge of the screen as well, right? So that would be a 2 by 2 image, so you should be allowed to sample that pixel there. So it's got to be less than or equal to include that, and then else you want to store in a transparent 000, which will probably just give you transparent pixel at the end. Well, probably a 0001. Something like that, I think. But that LDS only caches fetches for a single output pixel. Don't we want to parallelize over output pixels without reloading? Yeah. So, yeah, I think you're misinterpreting it. So, imagine we've got an 8 by 8 grid, right? An 8 by 8 grid. This is a 6 by 6. You've got a bunch of threads in it. You've got an 8 by 8 threads running. When you have... So this is currently a 3 by 3 in a sense. Right, you got 3 of these sort of black border ones, right? Okay. The lower resolution one. There you go into the destination image. And so for this 3 by 3, you're going to get a lot of overlap of these sample points, right? So we're using all of the threads initially just to pre-sample all of these sample points. Crap, I redid it. Yeah, all of these sample points. So it'd be this one here, 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 for instance. So you're preloading all these sample points across all of those sort of 8 by 8 threads that are available. But across this sort of whole 8 by 8, if you will. And then preloading that into LDS memory. And then after that, after all the threads have got here, they're then reusing that memory and resampling the pulling from the cached memory those pre-sampled coordinates, if you will. Maybe there's a better way to draw it. That image is a bit too noisy. Yeah, so if this one here, you've got this sample gets you these 2 by 2s, and this sample gets you this 2 by 2, and you're caching it. Oh, you think you get it right? Yeah, that's good. Yeah, so you're going over this whole sort of image, pre-getting all the samples for all of the threads that would ever be doing this combination. And then afterwards, all of these individual pixels will be doing their own sort of like grabbing of all of these. They'll just prefetch that one there, prefetch this one here, prefetch that one there, and then sort of do the weighted average, and that will be happening in parallel for, so this red one will be starting here instead with these, anyway, you get the idea. So that'll be happening in parallel. Yeah. Hey Alex, always learning something new here. Yesterday I was looking at how to create macros in a function that are only available there locally. I was googling macros I have no scope. Yeah. Yeah, you can undef it. Yeah, exactly. All you have to be wary of is just don't use a name which is already defined. If not, you'll get a compile error. But yeah, that's the way you do it. Okay, so I think then it's all of the corners of a, yeah, so in a source text or yeah. Got it. So I think that will be it. So you'll include all of those right up to the border. Okay. Right, that seems sensible. That's quite crazy. So we're trying to say, put a comment here so we don't, so preload into LDS the 16 by 16 source texture. So we're pre-sampling on every what do you call that? A boundary, pixel boundary. Preloading into LDS. Sampled from the pixel boundaries to get a bilinear that has been bilinear sampled from the pixel boundaries. I think that's basically a short and sweet way of saying it, right? Okay, good. Now this is where we get to recycle all of them. So that should never happen since it's a directly divisible. So you've got this sort of 1 by 1. 0, 1, 2. That's technically 3. Oh, what's it gonna do? Alright, so technically it's gonna sample in the middle. Yeah, maybe this is oversampling again. Alright. Because we'll never do... So damn confusing. We're never gonna sample from this point, that point, or that point, right? So again, we're kind of oversampling here, but that's okay. So I can write in here, to do, we are oversampling here in places we do not use. So let's get this bit here done. So, okay, so these are So our LDS coordinate, this did change. It is simply a... Yeah, and is it a 3 by 3 now? Damn it. So if it was a 1 by 1, sorry, so you got a 2 by, it'll go to a 2 by 2, but this, for a 2 by 2, there's 3 sample locations. So, oh, this is complicated. So there's actually maybe, there's an extra 1, I think. Because you want to get, yeah. But again, we might be able to compress it down later on. Let's just get it right. So let's just oversample and then we can figure it out later. So, anywho. So not doing 4 of these anymore. So to get where we want, so to start off in the middle, that would be a ×2 add 1. So you're inside the center of the 2 by 2. Then, okay. So the first one we get is 0, 0. That's 0.5, right? So we've got this sort of location here in the source space, meaning this gray sort of outline rather than this thick black outline. The thick black outline is the downsampled destination. Then you're doing take 1 and add 1 to get this 1 and basically the other plus and minus 1s to get these, right? So that would be, so essentially, I guess you could do +1 + 1, and that's a 125. You've got one with a minus, another one with minus, and 2 minuses, yeah? Okay, so that is not all the samples though. Oh no, that's all the samples. Beautiful. And then you just output the final texture color. So that would then just be a store texture 2D format 16, 16, 16, 16 float. So that would be in the destination texture image at pixel coordinate DST coord value of color. So I did put total color in there, but it's no longer total because the weight adds to 1, so it's fine. There's no need to do a division, right? So we should look at total color and just drop that. Crap. Okay. There we go. So we could say that basically the weight, you know, the weight note weight adds up to 1.0. So no need to divide by weight. All right. So I think this is all right. Again, we've got this sort of like oversampling we're doing here for things we're not actually going to use. Like we're never going to go use the directly up. The directly up directly left, directly right, directly down. So we could probably miss those ones in here and maybe squish this LDS space up a little bit more. But yeah, there's things to play about with. So what we're going to do now is kick this thing off for all of the MIP levels and just see how well it looks. And then we can improve it after that. Right. I'm just going to take a quick break and then we'll get the shader all plugged in, take a look at the texture viewer and see how well we did. Right, BRB. Right, welcome back everyone. So yeah, now we've got to kick this off. So we might kick it off for the first MIP just so we can have a little look maybe. You know, let's just write the code that does it for all of them. So we've got a bunch of MIPs. Yeah, so we're just going to do a ranged loop. So we'll write MIP. I don't know which one it is yet, from 0 to bloom MIPs take 1. Now we haven't got the constants set up right. So we need to, let's get them sorted out. Let's write the structure out here quick. And then we'll simply just right. So where is it here? So with this sample texture, so HCC sample texture, which is just gonna be the sort of like the bloom texture and it has access to all the MIP levels just for sampling. We then want to have then probably the one that we write to, so I guess it's write only. And it'll be in the 16.6. This is a storage texture, so you have to provide the format because of Intel up front. and this will be the destination texture. We also kind of need the source and the source dims, and I think we need the destination dims as well. And we also used the MIP, the sample MIP. So that can just be passed in as an int, like so. Okay, so we're going to move this to the shared header file so we can use it. Oh, for crying out loud, didn't I call it bloom down sample? Rightio. And I would take this bloom down sample, we fill it all in, and then kick off the shader. So let's go to graphics. We plop that in there like so. So we could like, if we put it out here, it means we can sort of like pre-initialize it once and reuse some of the variables and that. So we'll simply just say, right, bc dot, we'll just get the IntelliSense going. So sample texture, so that'd be a oh, we got to, yeah, we'll do it every time. We'll do this one every time because this will do the sync resource. So we're synchronizing as a read only. So this will be the GPU bloom texture. Rightio. Now this other one is like the destination texture. So it's the same one, but it needs to be kind of offset. So there's a way that we do this. It's a GPU. Yeah, I guess we can do, since we've already synchronized on it, it's just this plus whatever the MIP we're on. So what is this? The destination MIP? Right. So I guess this would be the source MIP. Yep. And then we say the destination MIP is source MIP plus 1. So that'd be, the sample MIP is source MIP. And now it's just a case of getting the dims. So I think there's a right, so for these I wonder if there is a shift right, there is as the so max. So maybe we could have like a dimensions, I don't know. So in the text view, you already do this, isn't it? Yeah, max 1. See, I think we should have a nice function for this, just because it's we do it a lot, and it'd just be nice to have one. So I think we should have a utility function called something like call it MIP dims. So you pass in your source dims and then a certain MIP level, and you get them back out. So we could probably, yeah, we'll just do it for texture 2D for now. So it is simply just a max of 1 with a bit shift right of dims with MIP, like that. Okay. Ooh. Shift right of a scalar parameter. Cool. So, yeah, it means inside graphics, we just simply use that, and you just say, right, the dimensions of bloom are... See, it's going to be doing unnecessary pixels when I refer to it as the full bloom. But if I just did the scene dims... that's the problem with it, isn't it? Yeah, okay, so we've got to do bloom dims. It'll do unnecessary pixels, but this is the way. So, DST MIP, and then source MIP. So we just got to make sure we do .xy here. And voila. Right, so now just got to launch the shader, so we've got to do a dispatch full script for the destination. Size the texture. So DST dims, this will be the bloom downsample. So unfortunately there's going to be as many dispatches as there are MIP levels, -1, but it'll mean that we have the nicer sampling than we do if we use the single pass down sampler. So there's going to be barriers placed down in between all of these and stuff like that, but maybe there's ways to optimize in the future. We just need to get something working and looking good. So let's give this a run. And I stupidly wrote the HLSL version of vectors rather than my own, because it's my muscle memory in it. So there we go. Thank you, compiler. So yeah, static variables have to be constant because they're not really supported in SpearV, so we need to say that it's in a thread group only. Nice. Undeclared identifier LDS base chord, because I called it source. Coordinate. Well, maybe I don't need to do that anymore. Right, so colors is source colors. Right, dot source colors, there we go. BC sample texture, why don't you... Function has sample with an implicit MIP. That's explicit. No. Why have you done this to me? That's an explicit MIP. Hence the... Oh, it's a MIP bias. Oh. MIP level. Okay. The compiler was right. Cool. That's good. So shaders are compiled and we're just looking at the... Right. So sillily... Yes, yeah, we thought it was a local variable, so... But it's inside a strut. And there we go. Right. I think that's looking alright. Let's give it a launch and check out the texture viewer. Here we go. So we're going to look at the floor, see something a little bit more interesting. We're going to then press F9, boost that boy up. We're going to bring the white levels down to something sensible. One is like, you know, regular sort of scene. So, all right. Clearly, something is wrong. Okay. That's not what we expected, right? Oh, here's why. We didn't initialize texture views. So we have a bloom texture and we need to instantiate the texture views. Yeah, ship it. That's what you want. That's bloom, right? So for some reason in 2025, we have no way to store to a storage texture at a particular MIP. So you have to create texture views. So our texture views are typically the index of the resource plus whatever the MIP is, but I haven't set that up for this bloom texture. So we're just going to go ahead and initialize that. So where do I do this before? It's like a MIP views. This is it. So this can kind of change. So I think we want to have like a max MIPS. Just be bloom MIPS capacity. So we'll pre-allocate these boys. Right, so we're going to pre-allocate a bunch of texture views that start after this one. So it just goes over all of, gets the resource, that bloom resource, gets the number of MIPS and just creates a bunch of texture views. And those will get properly initialized after. Reinitialized. Yes. Okay. So in the occlusion, right, reinitialize the views. Okay, bloom texture. Hang on a minute. Right, so we initialize it with the new bloom texture. And the number of MIPS we want is MIPS count. There we go. So that's just going to initialize all those texture views such that they point to each one of the MIPS individually. So then in the shader we can give it a texture view which points to that single MIP as if it's its own texture. Right, yeah, total black screen I guess is maybe worse. I'm planning on releasing the engine. Well, the engine is already kind of released. It's available to supporters of the channel, so people support via Ko-Fi, which is more preferable for me because more of the money is sent my way, but Twitch is the other one. For people who want to support via Twitch, I'm more than happy for that too. And those people get access to the code by joining the Discord and linking some stuff, and then it's it's via Git, so they just download it via Git, a Git clone, and they can run it on their machine and play with the code and things. So it's released in that sense. The engine is designed specifically for the game, whatever that game shall be. So currently it is a engine without a game, as people like to joke. But I've got some ideas that I'm thinking about. But I'm kind of letting the sort of technology, the graphics, and my sort of like research into this sort of really weird ellipsoid renderer drive sort of like a visual art style that I'll then turn into a game. I've got some interesting ideas that we'll be playing around with 2026. So the engine will probably, like the way I would probably like to do it is when you buy the game, you get access to the source code. That's what I would like to do. And then, quote unquote, the engine is released. People can make all the changes they want and that and give it to people who already have the copy of the game, as the license will say. But and you know, if people want to take the source code and make a game from that and ship it, they just have to come to me and ask me permission. That's probably the route I would like to take with this thing. Yeah, engine out a game. It's the way it is at the moment. But yeah, it's the way. This is how things work out. How long are we working on it? So it's probably coming up to about 2 years because I spent probably a year doing R&D, but this has just been in my spare time. So, you know, after work, 3 days a week, kind of like 4 hours each day, just work. You know, I did a bunch of like R&D because I didn't know what I wanted to do for graphics, and that's what it was initially. And I've written a whole bunch of different renderers that I've just sort of thrown away and just learnt from. So, yeah, you know, but so it's coming up to, it's a year and a half now. Yes, it's a year and a half now. So we're about 5 months away, I think, from 2 years. Yep. Good time? Mm-hmm. Source code expansion pack. Nah, just give it away with the game. Yeah, first call me. Maybe. Yeah, it's been awesome. Yeah, but you know, I learned a lot. It's not just there's many reasons to do this project, right? Improve my skills, ultimately drive to make something, have something perhaps I could maybe fall back on in the future, if I want to, or another avenue I could possibly go to in my career. The you know a you know maybe I could do this at the same time, you know, as working at some company or whatever. You know what I mean? So there's plenty of little like reasons to do this, and also share share my sort of experience along the way with people who are watching and along, right? So tons of little positives that I like from this, and hopefully we get something cool to show for it, and have some little funky game which is made with like ellipsoids and things. Normally, if you do something beneficial for society, it benefits your wallet. Yeah, I guess it could do. We'll see. I'm hoping so. I think these days, honestly, if you want to make a successful indie game, I think it's pretty difficult if you do not go public with it early. So obviously, the more I get on with this project, the more interesting it will be to more people, and the word will sort of build gradually that way, right? Right, so we went out the number of MIPS, I think, according to the call stack. The mighty call stack. Right. I did a silly. So... Oh. I think we get rid of that. But then that means I can't... Crying out loud. Yeah. Right, let's get rid of that. I don't think I can reinitialize something that's not been initialized yet. Meaning I might have to say if it's the first year. Ooh. What crap is this? Huh? Oh yeah, of course I gotta... Damn it. If 0... Resource debug name. But if the resource hasn't been... Okay, so what I've got to say is if it's a... Oh... Okay, I think I've got to make some temporary texture views. Texture view init temp. I've already got it. Right. So these ones... I see. MIP views, init static. MIP views, init temporary. Right. Okay, I see. So the static ones are expecting to be able to have the texture already made and allocated. Created as a Vulkan resource, so it can actually create them. Whereas the temporary ones are like, they're not made yet. Just make sure the sort of GPU resource is kind of around, and then later on we'll initialize all the Vulkan objects when the frame starts. So that will go here, and we'll say the word temp instead, TMP, and then we'll TMP that one there, which means we don't need all of this crap. Gotcha. Which means we don't need the texture that you come from. Or do we? We do. But, oh, we don't need the number of MIPS. Yeah, no. No, we do. Okay, good. Good. So, when it comes to then the reinitialize, but that's static. Okay, so we need another one of these where it's like temporary texture, so ones which have sort of like a frame lifetime or less. MIP views alloc. So they don't really actually allocate any memory, they're just sort of creating the texture resources under the hood, right? The Vulkan ones. And that will then... So the reinit ones, what did they do? So you got to have all of this business. Okay, gotcha. So we want to have this. So it's the reinit static. This one here, but for the temporary alloc thing. Radio, plop that in there. So temp alloc, I think it is. Temp texture MIP views alloc. That's the one. So it needs all of the bells and... Ah, crap, did I grab the wrong one? Oh, okay. No, it's fine. I just put the wrong stuff in the header file. So the texture and the number of MIPS. So we go over the texture. One OpenGL, because OpenGL is that old, right? Like it doesn't like it's got to go basically. You can do some really cool stuff in Vulkan, but it is crazy and annoying. It would be great if we had a more low level API. You know, once you understand how a GPU works hardware wise, Vulkan is, you kind of understand it more, but it's still like, you know, they do some really weird stuff in it that you wouldn't really need these days anymore. Like, basically, Vulkan is already old, and it would be good if we had a newer API already. I would just prefer if we already had one per vendor, you know, where we actually had it specific for the hardware. That would be cool. Hopefully not one per, you know, I'm thinking one per vendor. That would probably be better. Because the abstraction they come up with for Vulkan is just nuts. And it makes it harder to learn. When you have something that's tailored towards a particular vendor, there's more sort of like innards which are tangible. And you sort of see how the API maps to something. You know. They basically hide all of the sort of like GPU assembly stuff from you unless you use special tools made by the vendor. You don't even see that in the Vulkan API anywhere. So it all just seems like a weird black box. Texture MIPS alloc. So we get the texture and the MIPS. Go over all the MIP levels from 1. And we're looking at doing this function call here. Temp texture view alloc. Gotcha. So the MIP with the base texture. Amazing. Cool, so all it should take then. Right, I'm glad we got that sorted out. That's good. Temp texture alloc. Ah. Right, so now those temporary texture views have been allocated. Oh no. What have you done? Which one's doing that? 704. There. Temp. Okay, I didn't use the temp one. Right, so allocate MIP views, unhandled texture type A. Right, so something seems to not be initialized properly. So this is going to create it with... No, it won't. Ooh. Yes, this creates at 12 texture views. Maybe not 12, 11. That come after. Then... Yeah, maybe we plop this open in the... So it goes all the way down to the Vulkan code base and initializes the texture. And then that would be an unhandled texture type. So the resource type is not copied. I wonder why. So texture 2D is the resource type. So when you go into here, oh, I don't think I've used a temporary texture view yet. Yeah, I haven't used these yet. Okay, that understands why. So this, they have an alias, a null alias. Okay. Right, okay, so when we allocate the texture view, we need to make sure that we set resource type equal to whatever the base one is. Where is it? Aliased resource type. Okay. Jobs are good. Right. So we've got a scene rendering, texture viewer. Right, a bunch of bloom textures. Crazy. Why have I got so many of these? That shouldn't be happening. Why have we got 12 of them? Oh, did I accidentally create textures, not texture views? Because they say if they've got a... Oh... So I'm not setting the alias either. Alias resource ID. That's not been set either. Right, what other stuff are we missing? Base MIP and all that set. Yeah, okay, I think that... So yeah, we know if it's a texture view, if it's got the aliased resource ID set. And that was not set by the looks of it. Right, let's try that one out again. Okay, so we haven't got it being duplicated now, that's good. Okay, here we go. So let's bring this down a bit. Alright, it's black. No. Right, epic fail. So I've got some color modes here. White if non-zero. We're not going to anything right now. It's completely black. It will show white if not. So big problem there. Let's look at 1. And notice how the resolution is going down. Okay, so that's interesting. There's a clear happening, then a copy. Gotcha. What's the performance like? Right, so there's the bloom down samples. The first one takes 0.3 milliseconds because it's such a big old res. Then after that is 4 times less, I guess, then 4 times less than that, and so on. There's a bunch of barriers going on, so there's some breaks in between the dispatches there, but okay. Interesting. So let's do the same thing and go to the shader and write out a particular color, which we would. So I'm doing something super silly. So we're going to go ahead and output a color based on the coordinate. So we'll do like a divide float. No. So we'll do one of these, right? So it'll be casting into a float coordinate dot x divided by bc dims destination dims dot x. Same thing again, but for the y-axis. Alright, then it's 0, 1. Okay, so we try that out. We should see a green-red gradient. Yeah, we should see a green-red gradient inside every MIP level but the first one. And we don't. So that's a problem with the destination texture, maybe? We can open up in render doc to find out, or is it no dispatch index? That's alright. Okay, so it's a clear. Right. So I guess we'll open up render doc for this one because we'll be able to see which, well, the actual resources and check all their things, all their properties really easily. So we just boot up in render doc. We'll just do like a frame capture like that, and eventually we can close it. Right, it's just